Hello, everyone. My name is Leonid Startsev, and I work at Kotlin libraries team at JetBrains. That very same team that brought you these wonderful libraries as Kotlin X coroutines, Kotlin X serialization, cover, and many more. And so today we will be talking about best practices for writing and evolving your own Kotlin library. So to understand what's important about this task, we have to understand why library developers should care about compatibility of their libraries, unlike probably regular application developers. So let's consider the following situation. So we have an application and some library, version 1.5.1. So, and application uses this library and everything goes well. And then next release of this library came out, 1.6, and probably it has some method in it deleted. And so application author, when they update their library dependency, now sees some red code, some missing methods. They should waste some time on migration to the new version of library. And one can argue that this is part of developers' job sets. What we do, we are writing code, we changing method calls, adapting to new interfaces, and so on. But unfortunately, real life is more complicated than that. And the situation often looks like this. So when we have library A in our dependencies, not directly, but as a transitive dependency, we have some additional libraries B and library C. So what happens in this case when application developer updates library B that contains a dependency on a fresh version of library A with incompatible change? So library C wasn't changed, and it gets into in its class path a new version of library A without some method or some class with other incompatible change. And application developer starts to get linkage errors, like no such method exception and incompatible class change error and whatever linkage error you can imagine. And the problem is, in this situation, you can't do anything about it, because the problem is not in your application. You can't change any code in it to fix this problem. The problem is in precompiled library that depends on other libraries that had some changes. And so to avoid this situation, the author of library A should do his homework. He should care about compatibility, about incompatible changes, and it is part of their job, actually. So today we'll be talking mainly about Kotlin JVM. On Kotlin native, of course, it is also important to care about binary compatibility for klibs. But it has slightly different rules, so unfortunately, we don't have time to cover them today. We will be talking from the point of view of library developer, so what we can do to prevent these situations. And it can be not open source library. It also this advices are also applicable to if you develop some in-house library or in-house module in some complex system where parts can be deployed separately, and so on. So what we care about most is backward compatibility. So clients who expect older library version in the class path still work with the new one. And such backward compatibility can be broken easily by, for example, removing a declaration. And there are several types of it. So namely functional, binary, and source compatibilities. They're all slightly different. And functional compatibility is when you change or not change behavior of the function. So if in 1.5 library method did something A, like you fed the tiger, and in 1.5.1 it does completely different thing, like the tiger ate your fingers, this is probably not the most handy change to work with. And I think you should avoid these changes as much as possible to not surprise your users, unless it is some critical bug fix or security problem. So for source compatibility, it is also quite simple. When you had code that was perfectly valid in one version, and after updating the version, the code is no longer compiled with unresolved references or something else, then you broke the source compatibility. And it is not good, but also not bad either. So, and for binary compatibility, it is something that can be broken with no such method errors and everything else that end user probably cannot control by themselves. So such problems can happen even if you do not use problematic declaration directly. And the rules for binary compatibility on JVM are defined by Java Virtual Machine and their respective specification. So what do we want as a library author? Of course, we want full functional compatibility, with some exceptions for bug fixes, maybe in exceptional situations. For backward source compatibility, it is highly desirable, but it is not as problematic because when you break only the compilation of the code, someone can actually edit this code to fix the problem. And for backwards binary compatibility, it is, in most cases, an absolute must-have for the library because of problems with transitive dependencies and the ability to fix them for application developers. So you may ask the question, is source compatibility in Kotlin the same as binary one? So in most of the cases, it is true. For example, removing a declaration from the library breaks both source compatibility and binary compatibility. Same goes for changing method parameters list, adding an abstract method to an abstract class interface, and so on. However, there are cases when it is not true. For example, let's try to disrupt source compatibility but save binary one. There is this nice decoration in Kotlin standard library. It is called join to string. It has several parameters, all of them with default values. And let's say we have this parameter limit, which we decided to rename for some reason to max items. We can do this with preserving binary compatibility because bytecode on JVM doesn't store parameters names. And because we haven't changed its position or its type, it is a compatible change. But unfortunately, when we look at the source code, if someone was calling this method with named arguments, then they cannot call this method anymore with using limit name of the argument. They have to rewrite their code to using max items, using new name. And it is not very nice. Therefore, we will not rename limit to max items in Kotlin stdlib. The same goes for breaking binary compatibility without noticing it. So if you had some method with some already existing parameters, like here jump method with parameter length, let's say we want to add to it another parameter with a default value, the height. And so for source code, this change can easily go unnoticeable because we have add a parameter with a default value. So we do not have to change the call size of this method. We can still call jump with 1 argument or with 0 arguments. It will insert the default values automatically. But if you look at the compiled bytecode of these methods, we can easily spot the problem that the binary signature of this method has changed. Because before, it contained only 1 int argument and a specially generated bridge for default arguments, which also had 1 of them. And now it contains 2 arguments and 3 arguments in special syntactic bridge. And according to Java rules, this is an incompatible change because essentially we deleted one method and added another, and deleting a method causes no such method exceptions. So this is very dangerous type of the change because you can easily miss it because you preserve in source compatibility, But if you release such change in your library, your users probably won't be very happy. So there are other possibilities to break binary compatibility without noticing it, like extending or narrowing the types of parameters and return types, using copy and component and methods of data classes, and so on. So there is a documentation page on Kotlin Lang that describes definition of backwards compatibility and contains all these examples. And don't worry, I will give you QR code with a link at the end of the presentation. So to sum up, we can get into the situation when our code is green, when our tests are green, but people say that new release is awful because it breaks everything and people can't fix it by themselves. So preserving source compatibility while breaking binary at the same time is the most dangerous type of changes. So let's talk now about how we can track binary compatibility. So to avoid making such changes. Well, there are several methods to it. So first one is remember by heart what bytecode Kotlin compiler produces. This is probably a good solution for compiler engineers, but not so good for other people. So you can, of course, write integration tests. It is an adequate solution, but it consumes some time to write actually this setup with transitive dependencies, and it will also consume your CI time, and you have to spend some time on supporting it. So it's quite expensive in terms of developer time and machine time. You can also compare jar or AR files or any artifacts you want. There are some tools for it, like JAPI, CMP, for comparing jars that existed for a long time ago, but I have rarely seen it in the wild. So what else? Kotlin team offers you a great solution, which is called Binary Compatibility Validator. It is a special Gradle plugin that you can, as an offer of library, you can include it in your build. And when you do so, you can see that you have two new Gradle tasks. They're called API dump and API check. So let's see what this task is doing. So when you first run Gradle API dump, you can see that there is a new file in your project structure in the special folder called API and has API extension. So if we open it, we'll see the following. So imagine in our library we have this class tiger with one function now. When we open API file, we can see the contents of it resembles public API of this class. So we have the public class with a full qualified name, we have its functions, and something that you should also remember about. It has a public constructor, yes, because even if we haven't declared it in Kotlin, we have default constructors in Kotlin, and so we have public constructor without arguments. And if we, at some point, write that Tiger has a constructor with another number of arguments, it will be also incompatible change. And so by running this task, we just have bootstrapped the validator. So it is as simple as adding plugin to the build script, then generating baseline.api file with API dump task, and then you have to commit this file to your version control system. Now, what does the other task, API check, do? So if we make some changes to the code, like here, adding another parameter to funMal, so we already know that this is binary incompatible change, and when we run API check task, we can see that binary compatibility validator actually tells us about it. So it takes the current API dump and compares it to the API dump that is on the disk that we committed to the control system. So then it sees that these dumps are different, and it shows us the difference. So we had previously we had funMal without arguments, and now we have funMal with one argument. And so it tells us that API dumps don't match, and that we should do something about it. So using it during development, also quite easy. If API changes are unintentional, that API check task, which is by default the part of Gradle check or Gradle build, it will fail your build. You can see this failure on your local machine, you can see it on CI, and take measures about it. And if you want to intentionally make API changes, like adding new public class or new public method, you should just update your API dump and commit these changes to .api file, and then send it as a part of your review or whatever process you have. So you should remember that a binary compatibility validator is quite a dump tool. It doesn't actually tell you if APIs are compatible, it just tells you whether they were changed or not. So as a rule of thumb, you can assume that if API dump contains only added lines, then API is compatible because you only added a new method to it. But if there is some changed or deleted lines, then it is most likely incompatible and requires attention from the reviewer or from the author of this pull request. And hooray, a new function in the recent release of binary compatibility validator is that we added Calip validation there. So now you can validate API not only for JVM and Android parts of your library, but also for native and iOS ones. It has a different .api file format, but you can use it just in the same way. You just need to enable this in your build script. So another tool that Kotlin provides you for library authoring is explicit API mode. So the reasons for this mode are the following. So as we all know, that by default, Kotlin decorations are public. It wasn't always the case. So in Kotlin before 1.0, all decorations were actually internal by default until some time. But after careful studying of Kotlin use cases and Java code bases, it was decided that public occurs a lot more often than private, like 2 to 5 times more often is the code bases examined, including Kotlin compiler itself and IntelliJ IDEA. And indeed, this changed this decision that all decorations are public by default. It is very convenient for application developers and for IntelliJ IDEA developers and for everyone else except library developers. So imagine if we have this class and then we want to do some refactoring with it. We want to extract method. So we extracting our string literal or whatever else to a separate method, and we sending this change to review. So what reviewer sees? We know that fun meow with loudness is public API because, well, it was already there. But what about a new function, meow once? Was it intended to be public? And the author of this refactoring simply forgot to add it. Was it intended to be private and implementation detail? And again, someone forgot to add private to it. It is not clear for the reviewer, and it is easy to forget while doing it yourself. Of course, a binary compatibility validator can track these changes and it will warn you about them. But why we should have to wait for CI failure or for build failure when we can do it quicker? So when you enable explicit API mode in Kotlin compiler, it will tell you right away that all decorations, they have the visibility must be specified in explicit API mode. And it will also offer you a handy quick fix to make this change to add a public modifier. So it is quite convenient to not wait for API check task failure or for CI build failure, and to be able to fix this problem right away in IntelliJ just after you roll this function. Another part of this mode is also related to functions and refactorings. And it's comes from the fact that we have very nice feature in Kotlin, namely type inference for function return types. So if we write the function in the following way, that it is equals to some expression, Kotlin compiler can automatically deduce a return type for it. Like in this example, we write meow once equals meow, and then the Kotlin compiler automatically deduces the string type for it. So we don't have to write it down. Again, it's very convenient for application developers and very convenient in day-to-day life. But unfortunately, code can change, things can change, and we can accidentally change the return type. So if we call some function that returns, for example, char sequence instead of string, the result type of our meow_once function will also change to char sequence. And this is, of course, also a binary incompatible change from a JVM point of view. So again, instead of waiting for API check to fail, we can demand an explicit return type. So an explicit API mode return type also must be specified explicitly. And we also have a nice quick fix for it in IDEA. So to sum up, explicit API mode protects you from accidentally public declarations, protects from accidentally changing return types, and all diagnostics have IDEA quick fixes for the local place or for the whole file. And enabling it is quite easy. It is not a separate plugin. Whatever is just a setting in the Kotlin block in the build script. You can call the function explicit API or use a enumeration. So by default, all these diagnostics that require explicit return type and explicit visibility, they will produce compiler errors, which is maybe not that convenient if you already have a big project and you want to introduce explicit API into it. So for these cases, we have also a warning mode that will, well, produce warnings, as you might expect. So, and the last thing I can recommend you is just using the good old all warnings as error settings. There are several warnings that can affect your library and your code, such as unused parameter, for example. If you added a parameter to a function, released it, and then find out it is unused, you can take it back from public API because it will break everything and you have to live with it. So it's better to catch unused parameters as early as possible. Same goes for extension shadowed by member and a lot of other warnings. So it is quite a useful setting. Unfortunately, we also write tests. And for tests, it may be convenient to just prototype, experiment, or write different things. And when you run the test in your development iteration, the additional errors may cause delays and unnecessary pain. So what I personally use is I enable all warnings as error setting only for main production sources. And for the test sources, for compile test Kotlin task, you can leave this setting as false, as shown on the slide. So all these three tools, binary compatibility validator, explicit API mode, warnings as errors mode, are mandatory for every Kotlin X library. We use them in our day-to-day life, and we are quite happy with them. And I can only recommend you do the following to better keep track of everything. So now we have talked about how to track binary compatibility, but we also have to talk about how to remove things in case we need to do this change. So we all know that there are some deprecations. For example, let's take a look at how deprecated in Java works. So if we want to deprecate this method, so people won't use it anymore, we can write a new method and assign annotation deprecated on the old one. But unfortunately, deprecated in Java has some flaws. Like you can often see such code as on the slide. It doesn't tell you why this method was deprecated. It doesn't tell you the reason, and it doesn't tell you what you should use instead. Of course, you can write all this in Javadoc with a special deprecated tag. But this message, it is rendered in a special way. You can see that IDEA renders it in the very bottom of this pop-up by default. And the regular error message, even with -extreme deprecated, says that this method is just deprecated for whatever reason without giving you the details. So Kotlin decided to fix that. And in Kotlin, annotation deprecated has additional arguments. So we have message, we have replace with, and we have deprecation level. Let's see what these parameters do. So obviously, message just allows you to write a message with a deprecation reason, or with some additional information you may want to provide to the user of the deprecated method. And replace with allows you to specify a replacement for this. So now when we see this deprecated method in IDEA, we can clearly see the reason why it was deprecated. And moreover, this reason is also printed during the CI build. So it is not a solely IDEA feature, it is a feature of Kotlin compiler. It is able to parse these messages and print them while you compiling your code from, say, command line. And of course, we have nice replacement actions in IDEA. You can replace this particular usage of the method, or you can replace usages of deprecated method in the whole project directly. If you specify a proper replacement with replace with, users of your library likely would be able to migrate very quickly by using just replace usages of something in whole project, which works quite reliably in my experience. And the last argument is deprecation level. Well, warning, as you might have guessed, produce a regular CLI or ID warning, which will be turned into an error with a -v error. And deprecation level error causes a compilation error. But we also have a third deprecation level called deprecation level hidden. So what it does, it makes the method invisible for auto-completion, invisible for both Kotlin and Java compilers, but this method is not deleted from anywhere. It's still in the quest file and in your API. And by assigning this deprecation level, you can actually delete the function without deleting it. So for new users of the library who depend on it directly, they won't see this method, they couldn't use it. So they are forced to use the new method, the better one. But in these cases, when your library got via transitive dependency to some old client, nothing will break, and the library would work as it worked before. So by gradually raising deprecation level, we can naturally form a deprecation cycle. So first you have to deprecate method with warning, then you have to deprecate method with error level, and then you can hide it. So the question is when to raise this deprecation level. So the answer is it depends, and it should be defined by your compatibility policy, whether you follow semantic versioning, whether you follow some other versioning, and for example, whether you allow to be method deprecation level raised from warning to error in the minor release, or are you considering this breaking change that requires a major release raise? It is depends on you. So, and the last thing we are going to talk about today is how to evolve, how to add new things to a library, because we should do it. We can delete and deprecate everything, we should also add the new things. So the thing is, one library may have different flavors of API. We of course have stable API, we can have deprecated API, we can have internal API if we need it for some technical reasons. And we can also have experimental API. So why would you want an experimental API? You can have a different compatibility policy for it, for example, which allows for breaking change. Or you can have a faster deprecation cycle. Or you can leave yourself a room for semantic changes. And by doing so, you will be able to iterate quickly based on user feedback without needing for releasing major version of the library with deprecations and everything every other week. So how can we define an experimental API? There is a special annotation in Kotlin start library. It is called requires opt-in. And as you can see, it also contains message and the level, quite similar to deprecated, with message also being the reason and level also as error or warning. So when we want to define our experimental API, we use this annotation on another annotation class, which we can give a proper name, like, for example, for stdlib and unsigned types, it is experimental unsigned types. And then using this annotation, we can mark all these classes that experimental API consists of, like, for example, unsigned byte array. So what user sees will be on an attempt to use such declaration. So if it was an opt-in with warning, user will see a warning, like with byte array, see it's marked as yellow, so it is a warning. But for example, for a new base 64 class, which is also available in stdlib, it is marked as experimental encoding with requires opt-in level error. So user sees error when trying to use such declaration. So what can we do about it? Let's say we are writing some library of processing something, and we want to use Kotlin stdlib's base 64 or 64 and unsigned byte array. So we write our function, process values, and then we can mark it with the very same annotations, experimental unsigned types and experimental encoding API. In this case, client of process values will see the same warning or error. And the reason for it is quite simple. Imagine if base 64 is deleted from Kotlin starter library. Then your function, process values, will also be broken because you cannot call it anymore without base 64 class. You will get a no such method or no class defined error. Yes, so we have to warn our users about possibility of changes to base 64 and unsigned byte array, and we are doing so by placing experimental unsigned types on our function too. So there is other possibility to get rid of these warnings and errors by doing an opt-in to these annotation classes. So by doing so, when we call the preprocess function, we won't get any warning or error whatsoever. But it doesn't save you from the fact that if base 64 is deleted, then this function will also be broken. So think twice before doing that, and if you opt in not into annotations that you can control, you probably shouldn't do that. So to sum up, always prefer propagating usage over non-propagating usage. So use propagation when experimental types are a part of public declaration. If experimental declaration is an implementation detail, then you still should propagate it up to public if it is a declaration from dependency, like stdlib's experimental unsigned types. It is possible to opt in if it is experimental annotation you wrote yourself. So in that case, you surely know when you are going to delete it, and if you are going to delete it, how to migrate. And do not use module-wide opt-in that is available via command line arguments to the compiler. This is also not for you. So to conclude this talk, we can form something called a declaration lifecycle. So first, any new functions in new API, any new classes will be likely on experimental stage. So by marking them experimental, you can get a fast feedback loop from your users. You can iterate on the design quickly. You can change parameters, change parameter names, add new classes, delete the classes quite fast. After that, you either satisfied with your API shape and you promote it to stable, or you delete it and start again. And in stable stage, you can only do some bug fixes without changing any public API or any behavior of it, because once it's stable, you shouldn't touch it. And after it being stable, we can deprecate it if necessary after some release, or it can be stable forever. So that was all for today. Thank you all for coming. Our Kotlin libraries author guide is available with this link or with this QR code. Read it if you have time. And thank you. See ya.